Good morning. Today is going to be the lecture for Monday, March 30th. We're going to continue in class for picking up where we were at the right before spring break. So the first thing we're going to do is go over the exam. Trying to get this located in the right place. So we'll start with going over our exam. Try that again. Try this to make it work again. Okay, there we go. So just talk about the exam right quick. In terms of how did we all do, overall I was fairly pleased with the class performance. The average, when I adjusted the grades, the average was a 75, which that was something I was pleased about. The range of students on the performance was, we had a low of a 46, and several of you made in what would be the AB range, and a lot of you are very close to the B range in your score. So I was happy with your performance. Let me tell you how I modified it just a little bit. So when I went back and went over the exam, I kind of thought that maybe there were a couple of questions that were harder. There were more difficult questions than normally I have it on an exam. So the way that I modified this or adjusted your exam score, and you'll see it on the exams that I've sent out to you, is that there were the 25 multiple choice that were on the exam, and they were worth 3 points apiece. And then there were the 36 points, and that was a possible of 111 points if you put it together. The way that I adjusted the exam, instead of dividing by 111, I divided it by 105. And you'll see your score was adjusted by that. So I gave you a 6-point curve, is a simple way of thinking about it, or 6 potential point curve on the exam. So there were a couple of them more than usual that I thought that that were offered in this, what I would say, higher than average difficulty in the questions. So we're just going to quickly go over the exam and talk about some things that that may have caused problems. Again, this is not a live session, so you can't ask questions, but if you want me to bring this back up during the lab period tomorrow, where we're going to do the EOC problems, just let me know and I can bring these back up. The first one we did pretty good on. The second one, we had a first order reaction, and we knew that it went to 25% completion. So that means that 75% was left. So the fact that it was first order, we had to use the integrated rate law for first order. I said the initial concentration was 1 molar, so I took the natural log of 1, and that's 0. So you just had to put in the concentration that would have been at 42 minutes. So if 25% of it was lost, that means the remaining concentration would have been 0.75 if I started at 1, and then I put in the value for the time, and then you solve for K. And when you do that, you find that K is equal to the natural log divided by 0.75 divided by 0.42. That was a pretty difficult question, and a lot of you missed that one. We didn't work many examples where you solve for K like that, but C would have been the correct answer. All right, problem number 3 we did good on as a class. Looking at it, it was given this reaction, and if we plot the inverse of concentration versus time, it gives a straight line. So which one is that? That's a second order that you plot to give a straight line on that one. Number 4 was similar. What do you plot on to get a first order? Instead of looking at a graph, you just had to tell it to me verbally. Natural log of concentration versus time gives you a linear relationship. We did good on that one. Number 5 was another one that was probably a little trickier. So I considered it a difficult question. We didn't do good on it as a class. So you've got a first order decay. So I need to use the first order rate law or integrated rate law. And the half-life was a certain number of days. So from that, we could use from a first order reaction and find out what K is. So the half-life is equal to 0.693 divided by K. And after I solve that, that tells me the value of K is 0.818 inverse days. And then knowing that, I could go in and use the equation for the integrated rate law to find out what X would be at this period of time. So I put in the value of K, I put in the time, the passage of days, and the initial mass. Had to take the natural log of that. When I solve all of this portion of it, it gives me 4.215. And then that's the natural log of X is equal to that. So I had to take the anti-log of both sides, and it gives you 67 grams remaining. That was definitely a more difficult problem that I typically put in. And so this was another one that I gave you I thought maybe warranted a pass on. So that's the reason I scored it out of 105 versus the 111. Okay, so give you the balance following reaction. What is the rate with respect to H2? So here's our H2. So it's a reactant, so it's going to have a negative on it. There's a 3 stoichiometry, so it's going to be a negative 1/3 change in H2 over change in time. We did very good on that one as a class. Number 7, the order of the reactant with respect to Y. So I'm looking for Y. Here's the rate that's given. And with respect to Y, it's a first order. Okay, so if there's no power indicated, it's a first order in the system. Okay, so looking at the number 8, so you've got a reaction, and I want to know what happens if you double the concentration of the Y. What happens to the rate? So here's the concentration of Y, and the rate is proportional to Y to the 3rd power. So what happens if I take and double the concentration of Y? I have to take the 3rd power to that 2 in front of it, so it would be 8 times effectively the concentration. So the rate would increase by a factor of 8. We did pretty good on that one as a class. Number 9 says the combustion of ethylene yields these products. I give you the rate of disappearance of one of the reactants, so the rate of the O2, and I want to know how, using that piece of information, what is the rate of disappearance of the other reactant, which is the C2H4 is ethylene. So if we look at rate is equal to a negative change in concentration of ethylene divided by change of time, and I compare that to the rate of the oxygen. It's the negative 1/3 of the change in O2 versus change in time. So if I take and find out what this one is, it's simply 1/3 of what this value was. So I just divide it by 3 and divide it by 3, and I get choice D in the answers. All right, number 10 is how many half-lives are required to increase or for the concentration of the reactant to decrease to 12.5% of its original value. So we think about half-lives. Every time a half-life passes, we cut the concentration in half. So it goes from 100 to 50 in the first half-life. It goes from 50 to 25 in the second half-life, and it goes from 25 to 12.5 or 12.5 in the third half-life. So there's a total of 1, 2, 3 half-lives to make this change. So choice 3 or choice B, 3 half-lives. And we did good on that one as a class as well. Number 11 says the rate constant for a zero order reaction is given, and it says what is the half-life if the initial concentration is this value. So if we go back into the table that I gave you and look at what's the equation for the half-life of a zero order reaction, it's the concentration divided by 2 times the rate constant. So you put in the initial concentration and 2 and the rate constant, and you find that it's choice C, it's 0.31 seconds. Problem number 12. So we've got the isomerization. That means just a change of something, and what happens is the N and the C switch places. We talked about this particular reaction in our lecture. I tell you that it's first order, and I give you the rate constant in this one. And then I want to know what is the concentration after a certain time if the initial concentration is provided. So it's first order. This is going to be an integrated rate law question. The only trick to this one is that the time was in minutes and the rate constant was in seconds. So you had to take the time in minutes and convert it to seconds. Almost all of you picked this up, but a few of you didn't. You didn't look at the conversion of time or the units of time. So this is just another one of those questions that was maybe a little harder. So again, this is similar to the other one we worked. We know the rate constant K, we know the time in seconds, the initial concentration. We find what the natural log is. So it's a negative 6.724. So we have to take the antilog of both sides. And when we do, we find the concentration at the 0.2 minutes is 1.2 times 10 to the minus third molar. So choice A. Okay, so switching to the equilibrium chapter. So chapter 13 would be chapter 15. So if K is approximately 1, which is favored and neither is favored. So we did good on that one as a class. 14 says express the equilibrium constant for the following reaction. So you need to look at the things that were solids, and the ones that were solids don't appear in the equilibrium constant expression. So we're just going to use the things that are in the gaseous state. So it's products raised to the power of the stoichiometry over the reactants raised to the power of the stoichiometry. So a couple of you, I think, looked at that and decided that the force would cancel out, and you chose choice A. But it's not going to be choice A, because that would be K to the fourth root would be equal to this ratio. So we've got to keep those things to the powers of the stoichiometries in our equilibrium constant expressions K. All right, number 15 says, what is delta N for the following equation where we're converting Kc to K sub P? So a concentration-based equilibrium product to an equilibrium base. So if we look at the amount of product that we have 2 moles of gas. If we look at the reactants, we've got a total of 4 moles of gas in the system. Delta N is products minus reactants, so it's a -2, and therefore choice C is the value with that one. All right, so 16 says the equilibrium constants given below determine the missing constant. So I gave you this expression. Okay, so H2 plus Br2 yields HBr, and actually I just see there's a typo in that. It didn't change what we did, but it should be, to make it balanced, this needs to be a 2 in front of this, guy. So let me correct it at this point. Okay, so this would need to be a 2 to be correct, and this would need to be an 8. But based on the equilibrium that you had given to you, what is the equilibrium for the unknown in the system? So I need 4 times what's in equilibrium number 1 up here. So what I need to do is multiply it by itself 4 times, or take it to the 4th power. And if you take 3.8 times 10 to the 4th and multiply it by itself 4 times, or take it to the 4th power, you get choice D, 2.1 times 10 to the 18th. Okay, so number 17 says, for the following reaction, the value for K sub P is given. What is the value of K sub C? If I look at this reaction and I look at the values, the value for delta N is everything's in the gaseous state. So it's 3 moles minus 2 moles. So the value for delta N is a +1. And the equation says that K sub C is equal to K sub P divided by RT raised to the delta N power. So I put in the value for K sub P, put in the value for R and the temperature, positive 1 power, and I get choice D out of it. All right, problem number 18, determine the value of K sub C for the following equilibrium. So I've got the equilibrium concentrations of all the products and the reactants in the system. So I simply need to write out the K sub C expression, products over reactants. So the products squared, the NH3 is ammonia. The reactants are the nitrogen and the hydrogen gas. The hydrogen has to be the cube because of the stoichiometry associated with it. And now you just simply plug in these molar concentrations, make sure you raise them to the power. You got to square the NH3, you got to cube the hydrogen, and you find out that K sub C is 0.11 or choice A in the system. All right, number 19, determine the equilibrium constant or concentration for O2 if Kc is given and its value is 1.5. So the reaction initially contains only O2. So if I look at this one, I've got a solid and a solid. So the only two things that are going to appear in the equilibrium expression are the O2 and the SO2. So K sub C is going to equal to SO2 over O2. So I set up an ice system. So I had the initial concentration. So I said initially that's all I had was the amount of O2. And it's going to go forward to lose X moles of it. It's going to form X of the SO2. So what I'm going to have left is X 2.9 minus X and X. And I know the changes that occur in this system. So if I look at this, that solve what the value of K sub C is 1.5, I've got X and 2.9 minus X. And if I just do the algebra, if I take and multiply the 2.9 over to the other side, so let me get a pen of a different color here. So I'm going to take this term and multiply it over to this side. And then I'm going to take the 1.5 and distribute it to both terms inside the equation. I get 4.35 minus 1.5x is equal to x. I solve it for x, and x is equal to 1.74. And now I plug this back in to find out what the concentration is. It was 2.9 minus 1.7 in a significant 4, and I'm left with a concentration of 1.2. That maybe was a little bit harder problem for a multiple choice, but it's certainly within reason of something we should be able to do. Every once in a while, I throw one problem that's harder than others, and I don't think they're unreasonable problems, but I try to balance those out. And maybe on this test, I had more of those types of problems than I did on others. But many of you got that problem right, and that showed you had a good understanding of this. All right, problem number 20 says, consider the following equilibrium. What happens if O2 is added to the reaction? So this is Le Chartier's principle. So in this, O2 is a reactant. It's in the gas phase, so that means it will change as concentration or amount changes. So if I increase it, the equilibrium shifts towards the direction of the products in the forwards direction. Okay, so choice B. 21 is a similar type problem. In fact, it's the same equilibrium. And I want to know what happens if the volume is increased. So if the volume is increased, it's going to shift to the side with the most number of moles of gas. All right, so why is it going to, which way is it going to go then? So I've got 8 moles of gas on the product side and 11 moles of gas on the reactant side. It's going to shift to this side with the most number of moles. So it's going to shift in the direction of the reactants, choice B in this one. All right, so going to problem 22. Says I have at a certain temperature, K sub C is given, and I've got an equilibrium, and then I've got a 3-liter flask, and I've got a certain number of moles of CO2, and 0.1 moles of O2, and I want to know how many moles of CO2 are present in the flask. So on this one, I know what, if I look at the things that I know in the system, I know K sub C, I know the CO2, and I know the O2. Now I was given the number of moles and the volume, so I had to calculate the molar concentration by just dividing those, but that's easy to do. We've been talking about how to do that. So we just need to take and solve for the concentration of CO. So if I just do the algebra to rearrange, the CO is equal to the square root of the CO2 squared divided by Kc and O2. You got to remember to take the square root of it. And if I plug the numbers in and do the math, I find that the concentration of the CO was 0.0616 molar. And then what I ask is how many moles are present. So to find the number of moles, it was the concentration times the volume. So I had to take that and multiply it by the 3 liters. So when I multiply it by the 3 liters, I get 0.85. If I took the fact that you had to solve for concentration or from the number of moles out of it, and then take concentration and solve for the number of moles, undo that at the end, this is just a typical problem. So that one, not that tricky, but it does require that you paid some attention to detail. But again, probably I don't like to have as many of those difficulty of problems as I do. So that's part of the reason that I gave you a couple of points curve on this one. All right, 23 says you have a reaction that's got an equilibrium constant, and then the reaction mixture contains a certain concentrations of these reactants and products. And I want to know what's going to happen to the reaction. So what we need to do is calculate what is Q. So we take and calculate Q by putting products over reactants. So our products divided by the reactants, and we plug in all the numerical values for those, and we find out that the value for Q is 0.27. The value for K is 0.33. That was a given in the problem. So based on that, it's going to shift in the direction of products to reach equilibrium, or in the forward direction, choice A. All right, so we just got 2 more of the multiple choice. So if we use the chemist rule of thumb, this is one I promised you that would be on the exam. So at 30 degrees, if it has a rate of 0.15, I want to know what it would be at 60 degrees. So the chemist rule of thumb is every 10 degrees that it doubles. So from 30 to 40, it doubles. From 40 to 50, it doubles. From 50 to 60, it doubles. So it doubles, it doubles, it doubles. So that means I would expect it to be going up, doubling. So times 2, times 2, times 2, or times 2 to the 3rd power, and you get 1.2 molar per second. Okay, so 25 says identify the change that always would shift the equilibrium of the right. So I've got this the system that's everything's in the gaseous state, and I want to know what would cause it to shift to the right. Well, if I remove a reactant, that's going to cause it to shift to the left, so it's not choice A. If I increase the volume, it's going to shift to the left because it wants to go to the sides with the most moles of gas. If I add an inert gas, it's not going to do anything to it. But if I add a reactant to the system, that's going to cause it to shift in the forward direction, and that's what we would want it to do in this case. All right, so going to the calculation questions, we did pretty good on these, I think, as a class. First one says determine the overall rate law, including the value of K. So we did something very similar to this in lab. And we did several examples of these in class as well. So we want to find out what is the order with respect to the NO2 and to the O3, which is ozone. So if I look at the sets of experiments, and if I think of these as, I can't write very small here, so let me change the size of my highlighter. If I think of these as 1, 2, and 3, if I compare 1s and 2, The concentration of the NO2 stays the same, but the concentration of the O3 doubles. So double the concentration and the rate doubles as well. So that means it's first order with respect to the O3. Now, if I compare what happens between 2 and 3, I've got 2.5 the concentrations of NO2, yet the concentration of O3 stays the same. So 2.5 the concentration and the rate increases by a factor of 2.5 as well. So they increase by exactly the same factor. So that means it's first order with respect to the NO2. So that means that both of the values are first order with respect to the reactants. So I can take any of the values and solve for what the rate constant is. So I just use the first one that says that K is equal to the rate divided by the concentration of the reactants to the order, which is both 1. So I took the rate constant of 1.42, and I took the concentration of each of the reactants, and I find out that the rate constant is 43 inverse seconds. So now the overall rate law, including the value of K, which is what I asked you for in this problem, is rate is equal to 43 inverse seconds times the concentration of NO2 times the concentration of the O3. And as a class, we did pretty good on that one. All right, so 27, you've got a second order reaction, and I give you this reaction, and I give you a rate constant that's on the system. So here is the rate constant K, and it's a pretty big number. I give you an initial concentration of 2 times 10 to the minus fifth, and I want to know how long would it take for 90% of the reactant to disappear. So that's an example for the integrated rate law, and we're looking for how long. We want to solve for time. I know this is a second order, so I just need to go use the integrated rate law for a second order. If the initial concentration is this 2 times 10 to the minus fifth, at time x, I want to get rid of 90% of it, so that means 10% is remaining. That means it's 2 times 10 to the minus 6. And most of you recognize this and set that up right. So for a second order reaction, it's the inverse of the concentration at times x is equal to the rate constant K times time. That's what we're looking for as our variable, plus the inverse of the initial concentration. And when I just solve for the time, I have to take and do some rearranging on these. So these are just numbers. So if I take and divide that out, this becomes this number, and this becomes this number. Then I subtract this term to the left-hand side, divide by K, put it down on the bottom, and I find the time is 1.5 times 10 to the minus 4 seconds. So it's a pretty fast reaction, and we know it is because this rate constant is a really large number. So this occurs in literally microseconds that this reaction would occur. So almost instantaneous. All right, so next problem is problem number 28. So we've got a first order reaction, and we know the rate constant for it at a certain temperature. So we know K1, and it's at 25 degrees, which is equivalent to 298 Kelvin. And I want to know what is K2 at 95 degrees Celsius, which is 268 Kelvin. And the activation energy is 55.5 kilojoules per mole. So that's equal to 55.5 times 10 to the third joules per mole. So this is the Arrhenius equation, and we're solving it for what is K2. So we put in the value for K1, we put in the activation energy, we put in the gas constant R, or the thermodynamic constant R. We put our temperatures in for what they are in terms of T1 in Kelvin, T2 in Kelvin, and everything on the right. So all of this stuff multiplies and divides to be 4.216. So I need to get rid of this natural log. So I take e to both sides. The e of the natural log would cancel that out. So e to the 4.261 is 70.88. And then I multiply by K2. And K2 is equal to 9.57 times 10 to the minus third, or times 10 to the positive third. And a great number, more than half the class got that right. So that was a very positive sign. All right, so that was pretty tricky math. So you got an understanding of algebra if you work that problem. That's what I want you to demonstrate you have. 29 says the equilibrium constant is given for the two reactions below, determine the missing value. So you had to take equilibrias 1 and 3 and find what it would be for equilibria 2. This is the one that's the question mark. Okay, so the things that I recognize on this one is that this product is only present in this one. So equilibria 3 is going to be used as written. But I see that I need to do something to cancel some things out. So if I look at the one that I'm looking for, this reactant is only found in one place, and that's on this side. So I'm going to take this one and spin it around. All right, so when I spin it around, oops, move my page up. I'm trying to do that. So when I take this one and invert it or spin it around, it now becomes AB. 2 yields A plus 2 B's, and its value for K is 1 over 59. And if I add those together, the A's cancel out, and the 2B cancels out with 3 of the B's. So what I'm left with is AB2 plus B yields AB3. And now I take these two values and multiply them together. So some of you set everything up right and said you added them instead of multiplying them, and you lost a couple of points for doing that, but you need to multiply them. When you do that, the new value of K was 8.1. All right, problem number 30 says you've got a reaction N2 plus 2 O2s yields 2 N2Os, and I gave you a value of K. The reaction only contains initially the reactants in the system, and I want to know what is the equilibrium concentration of the O2, or the equilibrium concentration of the O2 was found to be 1.55. What is the equilibrium concentration of the NO2? So this is kind of an ice problem, but you didn't have to solve for K because the equilibrium concentration is actually given to you. So you had to just set the ice up and then solve for the X to find out what the equilibrium concentration of the one reactant was. Okay, so reactant 1, reactant 2, product, the initial concentration of the N2, the initial concentration of the O2. There's initially none of the NO2. So minus X, minus 2X, plus 2X, because it's 1 to 2 to 2 stoichiometry. All right, so I know the equilibrium concentration of this O2. It was found to be this guy. This was the information that was provided. So it was 0.155. So 0.2 minus 2X is equal to 0.155. If I just do the simple algebra, that means that X is 0.0225. So just need to apply that to find out what was the equilibrium concentration of the NO2. And the equilibrium concentration of the NO2 is simply 2 times that, which is what we found X was, which is 0.045. As a class, we did pretty good on that one. Problem number 31 says you've got 2 PCl5s decomposed to form 2 PCl6 plus Cl4. And then you've got a certain amount of reactant put in the flask. You've got a value of K sub C, and I want to know what is the concentration of the product Cl4. So this is an ice problem. You've got the initial concentration. You don't have any of the products at this point. So it's a 2 stoichiometry. So I'm going to say minus 2X of it. Both of the other ones are 1 stoichiometry, so plus X and plus X. So at equilibrium, I'm going to have 0.125 minus 2X and X and X. And so the K sub C is products over reactants. So the P or P2Cl6 is what we said was X. The Cl4 was also X. The concentration of the reactant, PCl5, was the initial concentration minus 2X. but it needs to be squared because of the 2 stoichiometry. And what I see is that reduces to x squared over the same thing on the bottom is equal to k sub c. Now, if I recognize that some of you said, well, this is a quadratic and you solved the quadratic equation, and a couple of you did it and you had errors in your math, a couple of you did it and you did it correctly, but there was a shortcut you could use on this one. By recognizing both of these had squares on it, you could take the square root of both sides. And when you took the square root of both sides, it got rid of these squares. So then it became just a simpler algebra problem. So then I just needed to take this term and multiply it over this side. So we knew what k sub c was. It was 1.8. So square root of 1.8 was 1.341. So I took this term, multiplied it by the 1.341. So the 1/8 minus 2x is equal to x, and I distribute and just do the algebra to solve for x, and I find that x is 0.0455 molar, and that's equal to the concentration of the Cl4, which is what we're looking for. Yeah, that's a challenging, nice problem, but again, some of these are harder than others. Okay, so that was the exam. Again, you should have you received an email from me going over the exam, so or with a copy of your exam. I scanned all those in from home last night and made a PDF of them and sent them to you. So you should have those available to review as you went through this. So if you hadn't looked at that email, you can go back and open your email up, and you can look at your exam and go through and replay this video at this point. I forgot to mention that at the start. So we want to go through, and at this point, we've got about half of our class period left. I just want to continue in the notes. So we're going to continue talking about our material that's in chapter 16, and I'm trying to move things around just a little bit to get it to where I need it to be. All right, so just going back where we were in acid-base chemistry, and we're going to continue in that. So hopefully this will be the format our notes look in for the rest of the semester. And I don't know that I see a lot of value of sticking me here in the corner. So you see a live picture of me, but in our Zoom training, we were strongly encouraged to keep the class more personable by having this live view. So it's here. So if y'all can tell me at the end of the semester where you think that provides any value or not. I figure you've seen my face enough this semester when we were in face-to-face section of it that that's not really necessary. So I kind of see this as something that's in the way, but it is what it is. And I'm just going to minimize it and throw it up here where we normally would put the clicker button. Okay, so if I look at the thing that we were talking about last, is we were looking at this concept of Bronsted-Lowry acids and bases, and we were talking about proton donor and proton acceptor. That's was the last topic that we talked about, and we said that a Bronsted-Lowry acid is something that donates a proton, and a Bronsted-Lowry base is something that accepts a proton. And we worked on this system with the bicarbonate, and we said the bicarbonate system was something that could be either a proton donor in this case, or it could be an acceptor. It just depends on where it's what it's working with. So bicarbonate worked as an acid here by donating its proton. It can work as a base as well, where it accepts a proton, just depending on who it's reacting with in the system. Okay, so if we continue with that, we want to just look at some example problems. So we want to write the formula for the conjugate acid for each of the problems. So or these examples. So I don't remember if yours has in the notes or not. It probably does. So if we want to know for the conjugate acid in the system, keep touching something wrong on my pen and it takes off on me. If we want to know for the conjugate acid in the system, that means after the system has accepted the proton. So if I look at H, or the water molecule, and it accepts a proton, the conjugate acid would be the H3O+. All right. If I look at NH3, after it accepts a proton, so it would form the NH4+. Similar, the carbonate ion, after it accepts a proton, its conjugate acid would be HCO3 minus 1. So this is carbonate. This is called bicarbonate. And then finally, the last one, this is dihydrogen phosphate. Once it picks up a single proton, and it's the last one it can pick up, it forms H3PO4, which is phosphoric acid. Okay, so those are examples of forming the conjugate acid. So that means that all of these would be working as the base in a Bronsted-Lowry reaction. So all of these guys would be working as the base in the system. All right, the next example says write the conjugate base. So we're going to do the same things now, but we want to form the conjugate base. So it's form the conjugate base when it's going to become the acceptor. So that means that it's, instead of gained the proton, it's lost the proton. So if I take and strip a proton from water, it gives the hydroxide, the OH minus. If I were to strip a proton from NH3, the charge goes with the proton, so it'd be the NH2, the minus. If I strip a proton from carbonate, I find that can't happen. So because there's no proton that can be lost there. So this one is a no-go. It can't happen. Strip a proton from H2PO4, it would be HPO4, and then as I lose a proton, I lose one on charge, so it would be a -2. So this would be monohydrogen phosphate. We're starting on these, the acids. So on the left-hand side, everything would be the acid. So on the right-hand side, they forming the conjugate bases. So all of these are on the right-hand side. On these are the conjugate bases in the system. All right, so when we talk about strengths of acids and we look at the comparisons of those, we say that generically there are two different types of these electrolytes. So there are strong electrolytes where practically all of the molecule ionizes or dissociates. We talked about electrolytes being strong or weak back when we talked about ionic compounds. Now we want to continue that into acids and bases. So we have strong acids. That means that the acid would almost completely dissociate into the ionized form. In a similar method, you have a strong base where it's going to completely dissociate into the ionized form, which produces the OH minus ions, either through dissociation or reaction with water. And then on the converse side, to these both being the strongs, we have weak electrolytes. So that only means that a percentage of the molecule ionizes. And then when it's a partial ionization, we represent it with double arrows. And it can be either an acid or a base being a weak electrolyte. So the converse side of that is when we represent the strongs. With the strongs, we represent the strongs with a forward arrow. So an example of a strong acid, it would 100% dissociate. We would draw a single arrow, and that single arrow is representing 100% of the strong acid dissociates into the proton and the conjugate base. And the same would be true if it were the base. So if it were BOH, whatever B might be, it would be a single arrow, and it would be the B plus the OH minus. It's 100% dissociation in the system. Now on these weak systems, it's a partial. And if we represent a weak acid as the letter A, the partial ionization means that an equilibrium is established. So the stuff that we focused on chapter 15 about equilibria, it didn't go away. In fact, it's going to, if you struggled with that stuff in chapter 15, that test we just reviewed, I encourage you to really go back over and see what you missed. To do weak acids and weak bases, we've got to do a little bit of ice work in setting up these equilibria. So in a similar way, a base would react and be a partial ionization. It's not a complete ionization, so it would react to form the BH plus by taking a proton, and if it's reacting with water, it would kick off NOH minus from water. So we have things that can work as a weak acid or a weak base, but there's things that produce either the H plus or the OH minus, and it's a partial equilibrium, not like a full equilibrium. Now, strong acids, just going back what I just emphasized on the previous page, and I'll do this quickly. Strong acid simply means that it's a strong electrolyte. It's 100% ionized in water. What that simply means, if we think about putting an assignment to that or putting value to that, is that the concentration of the strong acid, whatever that may be, whether it's hydrochloric acid or nitric acid, that concentration is approximately equal to the concentration of the H plus in solution. So it 100% falls apart, so all the acid just gets converted into the H plus. And a similar thing is going to be true with a strong base when we look at those. But when we think about what that means, it simply means that whatever the concentration of the strong acid is, that equals the concentration of the H plus. And remember, I told you that H plus and H3O plus mean the same thing. Sometimes really the hydronium ion H3O plus is a representation because this guy doesn't exist in water by itself, but those two things mean the same. They're analogous to one another. The square brackets around it just simply means that it's molar concentration for something. So when I throw HCl into water and it dissolves in water, the HCl molecule doesn't exist. It completely falls apart in the hydronium ions and the chloride ions in solution. There's no intact HCl molecule, and that's true for any strong acid. So the common strong acids that we have are hydrochloric acid, hydrobromic acid, HI. So these are the halogens, and they're all of the halogens going down the list with the exception of the first one, HF. So the top of the 7A family is not as strong, doesn't form a strong acid, but everything below it does. And then we look at some other acids, which we call mineral acids. Common ones are nitric acid, perchloric acid, and sulfuric acid, H2SO4. It's an example of a diprotic. We'll talk about that a little bit further as we go on into the notes. So this is table 16.3 in your textbook, and this needs to be one that you just commit these 6 to memory. All right, now we look on the other side, the weaks. So weak means that it's a fractional dissociation. So it's a partial ionization. So most weak acids don't donate 100% of the proton to water. So sometimes it's much less than 1%. Sometimes it's more than 1%. But it's the key thing is that it's partial. It's not complete. And that's what do you mean when I say sometimes? Because what happens with weak acids is the extent of the ionization is dependent on the concentration. What does that mean? So let me go back to get a pen back up here. So if I look at a weak acid like acetic acid, so H, CH2, H3, O2, and it dissociates into H plus and the acetate ion. H2, H3, O2 minus, there's the acetate ion. All right. If that dissociation occurs, if I change the concentration, so if I were to change this concentration of this species, So of the acetate ion, because this is an ice setup, if I change this concentration, Le Chartier's principle says it would cause this equilibrium to shift to the forward as it increases, or in the reverse direction as it decreases. Um, so the extent of the ionization is actually dependent on how much of the acid's there. If it's a very low concentration of acetic acid, like if I made a solution that's 1 times 10 to the minus fifth, acetic acid may dissociate to 80 or 90%. If I had a solution that's a much higher concentration, like vinegar is about uh, somewhere between 0.5 and 1 molar, the acetic acid concentration in vinegar, the ionization of acetic acid in that is much less than 5%. So it changes with the change in the concentration. That's what makes weak acids and weak bases a little bit more complex. So if I looked at the example with HF, if I put HF in water, hydrofluoric acid, some of the HF molecules exist intact. In fact, most of the molecules are still there. There's only just a few that don't dissociate into, or that don't stay intact. There's only a few that do dissociate into the fluoride ion and the hydronium ion. But if I look at the balance here, most of them stay together. That's an example of a weak electrolyte or a weak acid. So the common weak acids we need to know, HF is a common one. Acetic acid is a common one. We just talked about it. Formic acid, that's the stuff in ant stings. Sulfurous acid. Now, sulfuric acid we just looked at. We got to understand the difference between the two. Sulfuric acid was H2SO4. This is H2SO3. And another common one that's an important one is carbonic acid, H2CO3. And then a common polyprotic acid that we see in biological systems is the phosphate system. So phosphoric acid is H3PO4. So those are some weak acids that you need to know by name. And these are just a small sampling of the number of weak acids. There's a lot more weak acids that are available in these systems. So the strength of the weak acid, how much of it is going to dissociate depends on what the anion is and the attraction between the anion and the H+. And typically we determine the strength by looking at what the equilibrium dissociation constant is with that substance. So if it's an acid, I look at the magnitude of the K that would be describing the dissociation from the weak acid. So this is a weak acid, losing that proton off to form the conjugate base and the hydronium ion. And we call that value of that K the acid dissociation constant, Ka. And similar for a base could react with water to pick up a proton, produce the OH minus. And if it's a weak base, we describe its ionization constant as a Kb, or a base dissociation constant. So the smaller the value for this ionization constant K, that means the weaker the acid or the base is. So if we think about something that's very strong and starting to approach 1 or even be larger than 1, and then if it's weak, the smaller that number is, remember it never can be 0, but it can approach 0. That the smaller that number is, the weaker that equilibrium goes in the forward direction. The more it favors the reactants than it does the products. So values for weak acids, something like a strong weak acid like HF may have a Ka value of something times 10 to the minus 1 or 10 to the minus 2. Acetic acid is something that's 10 to the minus fifth. And then you look at something like a much weaker acid like boric acid, it has a Ka of 10 to the minus 10th. So they can vary a lot. And that means that the strengths of these weak acids vary a lot. And their contribution to an acid-base equilibrium is going to change based on how much of this proton or the hydroxide is being made and available to that equilibrium. So the equilibrium depends on the strength of the attraction, which is related to this Ka value. And it's also going to be dependent on the concentration of it. So Le Chartier's principle says the more that you have the more it's going to shift that equilibrium in the forward direction. So this table gives us a comparison of the strengths of acids and bases. And what it ties together is the comparison of the conjugate in a system. So if we look at on this side, we have the acids, and on this side, we have the conjugate bases. And then things to point out is that the strength of the acid is the highest up here, and the strengths of the bases are lowest down here. So if we look at some comparisons of some different types of compounds, like one of the common strong acids is perchloric acid. It's the strongest of the mineral acids. The perchlorate ion, the conjugate base, is a very, very weak base. In fact, it's weak to the point it has no strength. And that's same true for all of these strong acids. So the ones that we talked about, the HBr, the HCl, sulfuric acid, nitric acid, all of those, the conjugate bases that they form here, they have no strength as a base. So it's exists as if they don't exist as a base in the system. But now when we start to move into the weaker acids, so something like hydrofluoric acid we mentioned, the fluoride ion is now becoming a base with a little bit strength of a conjugate base. And as we go further and further down the list, if we look at something like acetic acid, the acetate ion is a stronger base than the fluoride ion. Why? Because it's a weaker acid, that therefore the conjugate is a stronger base. And we get down at the bottom, if you look at something like ammonia, ammonia is a very weak acid, but the amide ion, the NH2 minus, is a very, very strong base in the system. So that's where the conjugates come into play. Everything works as a pair in the system. So when we look at the strengths and compare the ionic attraction, what happens is that with strong acids, the attraction between the proton and the conjugate in the system is a very weak attraction. So it's a complete ionization. Those things don't stick together very well. But with a weak acid, this attraction is stronger. So it's represented by the thickness of this bond. So here it's thin, it's representing a weak bond. Here it's a thicker, it's representing a stronger bond. It's a stronger attraction. It's holding them together more. So that means it's a partial ionization is all that can occur in the system. All right, so we describe this for acids as the Ka, and I mentioned this is a little bit earlier. So with Ka, we're describing the partial ionization of a weak acid into the hydronium ion and its conjugate base. And the fact that water is a pure liquid in this means that we don't put water in the equilibrium constant expression. So the equilibrium constant expression for an acid, the Ka, is going to be products over reactants. So the products are the hydronium or the H plus, and the conjugate base, A minus, and then divided by the concentration of the reactant, the concentration of the weak acid, HA. That's equal to the Ka. And again, sometimes we substitute in just H plus instead of the hydronium ion to have the concentration in these systems. All right. So here's the table 16.5. So this gives again, this is a partial list of some of the more common weak acids, and we can see how the magnitudes of the Kas vary in here. So when we describe the Kas, these acid dissociation constants, frequently we will describe those with a P function. So a P function just means the negative log of something. So pKa, which is listed in this table, is simply equal to the negative log base 10 of the Ka. And what it simply does is it gives us a way to represent large numbers in a simpler format. And it's a common things that we do with logs. Just keep in mind, every time you change an order of magnitude in a number in a P function or a pKa, you change a factor of 10 in terms of the number. So chlorous acid is a strong weak acid. It has a Ka of 1.1 times 10 to the minus 2, so its pKa is 1.96. Nitrous acid, HNO2, Ka is 4.6 times 10 to the minus fourth. pKa is 3.34. Going to something a little bit weaker, hydrofluoric acid, HF, its Ka is 6.8 times 10 to the minus fourth. So its pKa is 3.17. Formic acid is 1.8 times 10 to the minus fourth, 3.74. And I'm not going to go through the whole list, but just to compare formic acid with benzoic acid, we look at this pairing between these two. The difference is simply an additional CH3. So this is formic acid, and this is acetic acid. So the difference is this is a proton, here it's a CH3. But the presence of the CH3 makes this a much weaker acid on the loss of this proton. And we'll learn more about that when you take organic chemistry, where structure plays a role. So if I look at the value, this Ka is almost exactly an order of magnitude smaller than the one for formic acid. It's 1.8 times 10 to the minus fifth. This one's 1.8 times 10 to the minus fourth. So when I compare the pKa's, I see that it's exactly 1 pH unit smaller than. And if I keep going down, I'll see things that are just weaker and weaker and weaker. So hypochlorous acid, the common stuff that we put in swimming pools, is a pKa of about 7.5. Phenol, the stuff in mouthwash, is a pKa approaching 10. So its Ka value is a really small number in a system. And again, this is a partial list. That are literally hundreds and hundreds of different compounds that have can work as weak acids. There's thousands of compounds that can work as weak acids. So continuing, just to throw you a little bit more of a curveball, we have some things, and we've talked about these, things like that have more than one proton that can be given off. So we call these, we give them a unique name, we call them polyprotic acids. And a polyprotic simply means that it has more than one ionizable proton. So we've talked about things like sulfuric acid, carbonic acid, phosphoric acid several times through the course of the semester. Now we just want to formally put definitions to those and call them polyprotics. Now the different protons can come off at different strengths, or they can be equal. So we say something that has only one proton to be donated, we call that a monoprotic acid. Something that has two protons to be donated would be something like sulfuric acid. We call that a diprotic. And something that could donate three protons would be something like citric acid, or in our common example, it's phosphoric acid. That's a triprotic acid. Where anything that only has a single proton would be a monoprotic acid, like HCl. So when we say that the strengths can be equal or they can be different, what typically happens is that each time you remove a proton, it takes more energy to remove the second proton from the system. So if we look at sulfuric acid, H2SO4, it's a stronger acid than bisulfate after it's lost the first proton. So the loss of the first proton is actually a strong acid, but the loss of the second proton is a strong weak acid. Now, sometimes if you have sequential losses, the differences are very substantial. So I want to get a pen so I can write this out. So if I have something like phosphoric acid, and I lose a proton off. So if it loses this proton off, it forms the H2PO4 minus. And it can lose another proton off. It could form the HPO4 2 minus. All right, so every time I lose a proton off, this becomes a weaker and weaker acid. So with the case of the phosphoric acid system, the difference in magnitude is about 10 to the third. So this proton is about 1,000 times stronger than this proton. And if I lose the third proton off to form the fully deprotonated PO4 minus 3, the phosphate ion, by loss of a proton, it's the weakest of all of them. And it also is about 10 to the third times weaker than the one above it. But where this is a pretty strong weak acid, this is a terribly weak acid, but that makes this a very strong conjugate base, because remember those things were paired up as we talked about in the slides. All right, so when we look at the autoionization of water, in fact, I think this is going to be my stopping point for this video. I didn't quite go the full 75 minutes of the lecture time, but I got pretty close to it. We spent a long time doing the exam review, but we want to start in the next section. And on Wednesday's video, we're going to start with talking about the autoionization of water. So water is an example of something that can be an acid or base, and we want to talk about that relationship we have, and we're going to introduce something called pH going forward. But this would be a good opportunity, if you haven't read over the notes, read over the notes starting on this slide and going forward, or read this topic in the textbook. The other thing that you'll need to do is this afternoon I'll make the quiz available, and I'll give you until Tuesday evening to go through and do the quiz, which would be equivalent to the clicker questions for this week. And you'll have, or for this day, and there's going to be 2 or 3 clicker questions. There's not very much at all, but just go spend a short period of time and try to answer those clicker questions. So if you have questions, again, go to the discussion boards, post those, and hopefully we're going to figure out a way to get to this as seamlessly as possible. We still have, just reminding you of the timeline, and we can't slow down much in terms of trying to accomplish materials. We've got to get through about 5 more chapters, and we've got about 5 weeks to do it in. So or 4 more chapters, sorry. We're not going to stop and smell the roses very much at all. We've got to make through this. All right, so I'm going to call it stops on this video. If you're having technical difficulties seeing these videos, let me know. Put the things on the discussion board. If I need to change something in the formats, I'll do that. I had issues at home trying to save these, so I had to come into work, but I think I've got them in a format that's working okay. All right, so with that, we'll sign out on this one. Make sure you go do the quiz that'll be posted.